don't know why the board is in this condition, but I'm going to have to go ahead with this anyway. We'll do this kind of quickly. It's fairly straightforward. Okay, so for 2 flips of a coin, and given this problem in homework, everybody got this. Possible outcomes were heads, 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 tails, tails, heads, and tails, tails. Okay, now for 3 flips, what are the possible outcomes? Well, to list the possible outcomes, in yellow, I've listed heads, 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 tails, tails, heads, tails, tails twice. So heads, heads, here, here, heads, tails, tails, heads, tails, tails. And then on each of these, I've appended to the end a head. Okay, each of the ones in the first row. And for each of the ones in the second row, I've appended tail. So that the 3rd flip might be tails. Now, that gets all possible outcomes, and we can construct an argument that proves that, but it should be fairly obvious that it does. Doesn't mean that we don't want to know how to construct that argument, but we're not going to dwell on that right now because we have other things to do. Okay, following the same pattern, how do we list the outcomes for 4 flips? Well, I've got them here, but you ought to see if you can follow the pattern I used here and list 4 flips using the same pattern. Of course, there are other patterns you can use. If you don't use a pattern and some kind of a rigorous way to make sure you've got them all and that you're not repeating anything, you're likely to either repeat or miss things. Okay, so if we want to list 4 flips, what do? Well, we list all the ways 3 flips could come out. In purple, I've listed all the 8 ways 3 flips can come out, and then I listed it again. Now at that point, I hadn't listed anything else. The white symbol at the end wasn't there. But then I did the same thing I did previously, and I appended head to the end, and then I appended, and for all 8 listings here, and then for all 8 of these listings, I appended a tail at the end. And now I'm pretty well assured that every one of these is in the first place different, and in the second place, if I started with the right list and did everything right all the way down, there can be nothing missing. Again, that has to be argued, has to be proven. Okay, now there are other ways to list these. You can make a tree diagram. Most people have seen tree diagrams by now. You can list these alphabetically. Okay, now this list is alphabetical. Heads, 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 tails, tails, heads, tails, tails. It's in alphabetical order. This list isn't. You could sit down and list the 4 flips with the idea that you start heads, 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 heads. Alphabetically, the next one would be heads, 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 tails. And then the next one would be heads, heads, tails, heads, and that occurs somewhere in here. It better. Heads, heads, tails, heads. Okay, I have to append a head, and I don't, there it is. Okay, well, there's actually a pattern within this that puts them in alphabetical order, but I'll just say that had we, instead of putting the head on the end here, put it at the beginning, then, and then in the second row here, put the tail at the beginning, then the whole listing would have been in alphabetical order. And if we put the additional flip at the beginning rather than the end, and if this one was in alphabetical order, then this one would be in alphabetical order. And you can also prove that that would be the case. So alphabetical order is a good way to list them, but this doubling is also a really reliable way to list them. And this does show you very clearly why the number of possible outcomes doubles every time you add a coin. Okay, so it's very kind of important to understand that. Now, we proceed, and I've done this just for, well, for this case, we notice that there is just one way, and I didn't, yeah, something's gotten wiped out here, but this is the number of heads. Okay? When you flip two coins, you can get no heads, you can get one head, you can get two heads. You know, sit around flipping two coins for a while and count them up, you'll experience that. But everybody pretty much understands that. Okay, how many ways are there to get no heads? Well, there's just one. That's two tails. How many ways are there to get one head? Well, you can get head on the first coin and tail on the second, or tail on the first coin, head on the second. How many ways are there to get two heads? Well, just one way, you get two heads, right? So we could make a bar graph or histogram of this distribution where 0 heads has one way to happen, so we make a little bar here. One head has two ways to happen, so we make a bar here that's twice as high as this one. And two heads, there's one way for it to happen, so this bar is identical to this one. Now we go to 3 flips and we can do the same thing. We could get 0, 1, 2, or 3 heads. If you count them up, you see that there's still just one way to get 0 heads. Now there are 3 ways to get one head. Okay, exactly one head. That occurs here, here, or here. Okay, 1, 2, 3. There are 2 ways to get 2 heads. Here's a way, and here's a way. And there's just one way to get 3 heads. So we have this histogram. Okay, and ignore the green curve for the moment. Okay, if we do 4 flips, well, we can make the histogram. You should be able to make one yourself. Now, this green curve for each of these. The way I instruct people to make the green curve, and I didn't really do it, except I sort of did it with one of the curves, is the green curve should be such that the area under the green curve corresponding to each bar should be equal to the area of the bar. Now, in the first bar, it's clear that the curve, the green curve here, is lower than the bar almost all the way across, so the area beneath the green curve between here and here is going to be less than the area of this bar. I did a little better up here. I wasn't really trying to do it. I just slopped down the curves. I did a little better up here. The area that I left out of the first bar is equal to the extra area I get when the curve goes up here. So the curve has an area approximately equal to that of the first bar. And it actually did pretty well on the third bar, but the curve is all the way above the middle bar. So the area under the curve for the middle bar is greater than the area of the middle bar. Okay, and you can look at that and see here are a couple of bars where I did pretty well. Here's one where I again did poorly, but here's where I did pretty well, at least reasonably well, with this bar and this bar, especially with this one. Okay, well, when you construct these, and you're asked to do that in the homework, try to do it according to that idea, that the area corresponding to 0 heads, which goes from here to here, for the first bar, for that bar should be equal to the area under the curve between these 2 points. Similarly here, here, and here. Now, we're going to go on and calculate something called the standard deviation, and we're going to maybe relate the standard deviation to this bar graph and to this curve. And this curve, of course, has a name. You should know what the name is. It's your typical bell-shaped curve. It's also called the normal curve. Now, none of these, even if constructed according to my instructions, is a perfect bell-shaped curve. None of these is a perfect normal curve, even if you construct it the way I said. But if you keep increasing the number of flips, go up to 1,000 flips, not that you could list those, number of outcomes for 1,000 flips far, far exceeds the number of particles in the known universe. Okay? If each particle in the known universe was the known universe, you still wouldn't have enough. So you're not going to list those, at least not in the next hour. Okay. If you go up to 1,000 flips, and there is an easy way to compute, or at some point you actually want to approximate the number of possible outcomes. You could actually get that graph, and what you would have then would be a pretty good normal curve. Even if you didn't even try to, even if you just went through the center of each of these, you would have a pretty close to an excellent normal curve, pretty close to a perfect normal curve. So when you have just small numbers of flips, these aren't perfect normal curves, but by the time you get up to 8 or 10 flips, if you do this the way I say, you have really a pretty good normal curve. And I also comment there's actually a function. If y equals b to the negative x squared over 2, it turns out that that's a good model for the normal curve. And if you scale the graph properly, you get what we call the standard normal curve. And we'll construct that. But notice that this involves an exponential function of a power function. Okay? And that's kind of a tricky idea. And not sure how deep we'll get into that idea. We'll see how people do with it. So, kind of interesting. But the connection here is that this normal curve is really defined in terms of an exponential function of a power function. And that kind of emphasizes the fact that exponential and power functions occur in very powerful applications. We'll see more of that. Okay. They're really, well, I won't say anymore. Okay.